In this video, we'll be talking about transformations of the parent function f of x equals log base b of x. We will first graph log base b of x, whatever the base is, before you do your transformations. So the transformations are vertical shift. Whenever we have a plus c behind the log, notice this isn't part of the argument, this is an adding to the entire log, we have a transformation of shifting up c units. Similarly, if you subtract c, again from the function, not just the argument x, but the entire function, that shifts down c units. On the next two functions, we have a plus c and a minus c again, although the plus c and the minus c here are inside the parentheses. That means we're adding c to x, not the whole log, just to the x argument before you take the log. This is going to be a horizontal shift, opposite of your intuition or what you might think might happen. Plus c would seem like it goes to the right, but actually it goes to the left. The horizontal shifts always go opposite of what you might think, although the vertical shifts do exactly what you would assume they do. So on plus c we go left. For minus c inside the parentheses, we're going to move right c units. For the reflections, if we have a negative in front of the entire function, log base b of x, that reflects over the x. Axis, and if we have a negative inside with the argument, that's the negative on the x. That's also a reflection, but this time we're reflecting over the y-axis. Again, this was a new property that we learned in exponentials. We didn't cover that earlier in the semester. The vertical stretch and compress happen if you have a multiplier or a coefficient, a multiply by c in front of the log. Notice you don't multiply c to the x, the c is a coefficient out in front. If your c is greater than 1, that gives you a vertical stretch, meaning your vertical height on each point is going to get multiplied by the c value, which will make you taller than you normally are. Stretch. But if c is between 0 and 1, that's a vertical shrink or compress. Each of my y values or heights are going to get smaller as you multiply it by a c that is less than 1. Let's apply these transformations to some logarithmic functions. Our first example is f of x equals log x. Notice we don't have a base here, so that means I have an invisible base 10. Now we've already talked about picking points for logs is not an easy process. So what we're going to do instead is I'm going to find this function's inverse. And the inverse of log base 10 of x is the exponential function 10 to the x. Now 10 to the x is easy to find points for. When I plug in -1, I get a tenth. I plug in 0, I get 1. I plug in 1, I get 10. And I have 3 key points for this exponential function. But remember, that's not what I'm trying to graph here. What I would like to graph is the actual function log base 10 of x. Well, if I know these two are inverses, and I know inverses behave where the x and the y are interchanged, or they switch, my new points are going to be 1/10, -1, 1, 0, and 10, 1. Notice that I interchanged the x and the y values to get 3 key points. I know on my exponential function I have a horizontal asymptote at y equals 0. That means on my logarithmic function I have a vertical asymptote at x equals 0, or the y-axis. Now, when I'm trying to answer this question, what was being asked? I was asked to sketch log x. I was not asked to sketch its inverse 10 to the x. So all of this purple information that I have over here, it was helpful only to get the points for the log. So I'm not actually going to graph the exponential 10 to the x. I'm only going to graph the function f of x equals log x, the one I was asked to graph. So at 1/10 I have a -1, at 1 I have 0, and at positive 10 I have 1. Using these 3 points and knowing that I have a vertical asymptote at the y-axis, I can sketch this logarithmic function. Please do not sketch the exponential function. We only use this to our advantage to get the points for the logarithmic. On the next problem, I'm asked to graph f of x equals log of x plus 2. Notice the x plus 2 is in parentheses. What does the plus 2 inside the parentheses do? Well, that's a horizontal shift. It's a horizontal shift. Plus 2 moves opposite of your intuition, left 2 units. I used to have a vertical asymptote at the y-axis, or x equals 0. But when I move my vertical asymptote left 2 units, then not only the graph shifts left, but also the asymptote shifts left 2 units. So my asymptote is going to be x equals negative 2. I'm going to shift all of my points left 2, connect my points, follow my asymptote, and I have my new function f of x is equal to log of x plus 2. On the next function, I have log of x minus 2. Notice the minus 2 is not combined with the x in parentheses, so I'm actually subtracting 2 to the whole function, not to just the argument x, which means I have a vertical shift. And a minus 2 means I'm going down 2 units. Well, my vertical asymptote of my original black function was the y-axis, or x equals 0. If you take your vertical asymptote and shift it down 2 units, well, you really don't change your asymptote at all. It still stays the same asymptote at x equals 0. All I'm doing to the points is shifting each of the points down 2 units. Then I can connect my points, approach my asymptote, and the blue line does look like the black line just shifted down 2 units. On this last problem, I have f of x equals negative, or the opposite of log x. Negative means it's a reflection. Because it's out in front of the function, that's a reflection over the x-axis. So all of my points are going to be reflected over the x-axis from the original black function. So when I reflect over the x, at 1/10 comma negative 1 turns into 1/10 comma positive 1. If I reflect 1 comma 0 over the x-axis, it stays put at 1 comma 0. When I reflect 10 comma positive 1 over the x-axis, it becomes 10 comma negative 1. I can connect my points, approaching my vertical asymptote, and my green function should look like my black function just flipped over the x-axis. I want you to note that in each of these transformations, only one of them shifted your vertical asymptote. And the only one that shifted your vertical asymptote is if you have a horizontal shift. Horizontal shifts also shift your asymptote for logarithmic functions. If you look back in your notes, when we were graphing exponential functions, the asymptote was only changed for vertical shifts for exponential functions, whereas for log functions, the asymptote's only shifted for horizontal. So vertical asymptotes get shifted for horizontal shifts. Horizontal asymptotes only get shifted for vertical shifts. So this is the only time your log function's asymptote will be shifted, is for horizontal. We have one more example. Let's see if that's the same for the next problem. For f of x equals ln x, again, this is something hard to sketch using x and y values. So what I'm going to do is I'm going to cheat a little bit, and I'm just going to use this inverse. And I know the inverse. I can get the inverse very quickly because I know the base. There's an invisible base e, so the inverse is going to be e to the x. I can use -1, 0, and 1 to easily find some points for e to the x. To find e to the -1, I hit the second button, then the ln. See how there's an e, the little yellow e to the x there? And then I type in -1, hit parentheses, and that gets me 0.37. E to the 0 I know is 1, and e to the 1 is 2.72. Using this information, I can find 3 points for my actual function that I'm interested in, ln x, by switching the x and the y. Because these are inverses, I am being a little sneaky here. I'm using the exponential inverse function of the logarithmic function to find 3 points. So then I just switch the x and y values, and I have 3 good points for ln x. On my exponential function e to the x, I have a horizontal asymptote at y equals 0. So when I switch the x and the y, I have a vertical asymptote at x equals 0, or the y-axis, for the actual function I'm graphing. Only graph the ln x function, because that's what I was asked to do. I was never asked to graph e to the x. I only used that e to the x information to get my points. I was being just a little bit sneaky and getting the information I needed without doing too much effort. I'm going to go ahead and get one more point here. E to the 2, 7.39. Just so I have a little bit better graph, 7.39, 2. 7.39, 2. Now I use these points to sketch my graph. Don't forget to get close to your asymptote. Next, I'm going to graph these 3 transformed functions. On my red function, I'm subtracting 3 inside the parentheses. Inside the parentheses is a horizontal shift. -3 tells me I go right 3. Horizontal shift is opposite of your intuition, so that's right 3. If I take my vertical asymptote and I shift it horizontally, I'm shifting it to the right 3. My asymptote also shifts right 3. Next, I'm going to shift each of these points to the right 3. So off my graph a little bit. Connect my points approaching my new asymptote, and I have my black function, which is shifted to the right 3 to become my red function. For the blue function f of x equals ln of the opposite of x, notice we have a negative, and a negative is a reflection. I'm reflecting in this case over the y-axis because the negative's inside the parentheses with the x. My vertical asymptote used to be x equals 0 for the y-axis. If I reflect it over the y-axis, I still get the y-axis, or x equals 0. So my asymptote does not change unless I have a horizontal shift. So now I'm taking each of the black points and reflecting it over the y at 0.37, -1. When I reflect it over the y, I get -0.37, -1. At 1, 0, when I reflect it over the y, I get -1, 0. 2.72, 1, I reflect it over the y, I'm getting -2.71, 1. And at 7.39, 2, I reflect it over the y and get -7.39, 2. Connecting these points with my asymptote, approaching my asymptote, I have this sketch. And on this last function, f of x equals ln x plus 4, the plus 4 is being added to the outside of the function, which means I have a vertical shift. In this case, we're shifting up 4 units. My vertical asymptote, if I shift a vertical line up, I still get the same vertical line at x equals 0. Notice my asymptote did not change unless I'm doing a horizontal shift. So I take my black points that I had before, and I'm shifting each one of them up 1, 2, 3, 4 units. One, 2, 3, 4. Connect my lines approaching my asymptote. And that's the graph of ln x plus 4. Again, one last note. Only shift your vertical asymptote when you have a horizontal shift. Similarly, if you're doing exponential functions, you only shift your horizontal asymptote when you have vertical shifts. The horizontal and the vertical should be opposites. Vertical asymptote, horizontal shift. Horizontal asymptote gets moved if you have a vertical shift. And that concludes our lesson on logarithmic functions, where we learned about the notation of logarithmic functions. We learned how to change from log form to exponential and from exponential back to log. We learned how to evaluate logs without a calculator. We learned some log properties and how to graph logarithmic functions by using the exponential inverse points to graph the logarithmic functions and then transform.